Welcome back. In lecture 45, we will cover dynamic traffic assignment, and this is the final lecture in the traffic assignment module. So, the different concepts that will be covered in this particular lecture will be on dynamic nature of traffic, static versus dynamic assignment, then dynamic traffic assignment requirements, dynamic user equilibrium, then different dynamic assignment models, information required to run these models, and the process and solution procedure. And then we will look into the simulation approach, steps and parameters for running dynamic assignment models, and finally model validation and calibration process. So, to start with, of course, traffic is dynamic, but whenever we are developing the assignment models for unique equilibrium solutions, and then we start with certain assumptions. For example, the traveler has full knowledge of the generalized cost of travel on every link and route in the network. So, we call it a perfect information assumption. And then we also consider the delays on links which is used which we model using a function which is a function of flows for that particular link only, and we call it a separability assumption. And finally, there is a steady state assumption which says that the demand and flows during the model period do not change over time during that period. So, these are the different assumptions that we start with, but of course, traffic is dynamic and the demand varies over time, and there are real capacity constraints, and this capacity constraints lead to formation of queues at the intersections or the bottlenecks or any kind of bottleneck, and then it prevents traffic reaching their destinations during the model period. So, these are the issues that we really face, and these queues remain and they continue to grow. When the demand increases, the queue also increases, and when the demand actually comes down, then gradually the queues also come down, and ultimately the queue doesn't exist. So, this kind of queue formation and this nature of traffic actually doesn't gels with the assumptions that we have made for static equilibrium. So, new improvement assignment methods should consider certain characteristics, like we should consider the real capacity constraints of a particular corridor or a particular path or even a link, we can say. The storage capacity of links to handle queues, like how long the queues could be and and what effect it will have. Then queues remaining at the end of the modeling period, and some of these queues also spills to the next time period. So, that has to be also considered. So, these are the things that needs to be considered when we develop a dynamic traffic assignment model. So, let us compare, or let us rather look into both static models and dynamic models and see the basic differences. So, in terms of travel time and congestion, so in static model, when we are doing static equilibrium assignment, we are assuming that the travel time is more if volume to capacity ratio is greater than 1. Now, this is fine, but at the same time it is not directly correlated with any actual, it is not directly correlated with congestion. That means we are not considering speed, density or the queue length of a particular corridor or at a particular link. So, we are not considering all this. So, in a dynamic model, there is direct linkage between travel time and congestion, and we assume that if a link outflow is lower than the link inflow, then link density will increase. That means the density of this in the fundamental equation of speed, flow and density, their density is actually taken into consideration, and speed will decrease, resulting in increased travel time. So, that is the assumption. So, we are considering density over here. And congestion, when we are looking into the congestion spillback effect, we are not considering any kind of congestion spillback in the static model. We are just considering congested condition because of increased volume compared to capacity, but we are not considering any kind of congestion spillback. But whereas in the dynamic model, we would be considering this congestion spillback, and we also say that congestion at the exit node where there is a reduced link outflow is propagated upstream through the link onto the next link. So, this is something which which is considered in a dynamic model. And then the FIFO rule, first in first out rule, this holds true for both dynamic and static models. The difference is all vehicles traveling on a link experiences the same travel time in the static model, whereas in the dynamic model we assume that all vehicles entering a link at a given point of time experience the same travel time. So, that means the basis of dynamic equilibrium is whenever the vehicle is entering into the link and any other vehicles entering during that time period or that small that segment of time, for them the travel time would remain same, and we also assume equilibrium for that time period. So, that becomes the dynamic equilibrium. So, in addition we also say that the lane separation part, no distinction between traffic conditions on different lanes of the same link. So, because the function does not allows that, the vehicle density function. So, in the other case, in the dynamic model, it distinguishes between different lanes on a roadway. So, if we have a high occupancy vehicle lane, means maybe a bus lane also, we can model it differently from a vehicle lane. So, Haydaker and Addison had identified certain requirements for developing a dynamic traffic assignment model. There are some key points. The first being positivity, that means non-negative flows on the links, paths, strip matrices and cost are not there. So, that is the first thing. Then flow conservation requirement is satisfied by the model, like most models. Then FIFO behavior is maintained as we just discussed, and it is also used for estimating delays as well. And then minimum travel time, flows do not propagate instantaneously, and then there is some travel time to it, and then finite clearing time, no queues at the end of the modeling period, there is no indefinite delays. So, that is another assumption. Capacity wise, there is strict capacity constraint and actual flows cannot exceed it even for a short period of time. So, that is another assumption, that is we cannot exceed capacity to at any point of time. And finally, causality, that is delays result from what other vehicles have done and not what they will do in the future. So, that basically means in static equilibrium we are estimating that what kind of delays will or change in the vehicle density function will happen when capacity will increase, and accordingly equilibrium was attained. But in dynamic equilibrium we only considered the previous flows and as per what effect it has got on the delay. So, what kind of congestion it is creating, and that will affect my decisions in the subsequent stages. So, that is what is being tried to explain over here. So, in dynamic equilibrium we can actually modify Wardrop's equilibrium expression a little bit. So, if travelers choose route as well as time of departure, then what we can say is under equilibrium conditions in networks where congestion varies over time and travelers can choose their time of travel, traffic arranges itself so that the total cost associated with travel on those routes that are used by travelers at that time when they are used are equal and no greater than those of any route at a time when it is not used. So, it is more or less the same equilibrium concept, but only thing is we are introducing the aspect of time, that is for that particular point of time. Whenever a particular traveler chooses a route, then for that time, that based on the condition in that particular link or that particular path, the traffic will arrange itself and that will lead to equilibrium conditions. So, that is what is being said in dynamic usual equilibrium. So, dynamic assignment models are of two kinds. One is called a preventive dynamic assignment or dynamic en route assignment, and reactive dynamic assignment or dynamic equilibrium assignment. So, you can understand preventing dynamic assignment or dynamic en route assignment means there is something which is the equilibrium is obtained during the process, whereas reactive dynamic assignment or dynamic equilibrium assignment actually is assessed when we assume that at the end there is equilibrium and then we actually assess it. So, we can say during each time period the corresponding fraction of the demand is assigned to the currently available paths for each origin destination pair according to the probabilities estimated by the route choice model. So, this is the first thing. So, and then drivers can be allowed to dynamically change route instantaneously if a better path from their current position to the destination becomes available. So, whenever initially a particular driver or an individual is assigned to a particular route based on the probabilities of route choice using that kind of data that is available, but if during that particular process, if a new path becomes available which is much better than the previous path, then drivers can dynamically change their route as well. So, that is what is preventive dynamic assignment. Whereas in reactive dynamic assignment or dynamic equilibrium assignment, path flows are determined by an approximate solution to the mathematical model for dynamic equilibrium conditions. I have not included the mathematical model, but basically it is similar to the Wardrop's model, but it assumes that the speed will be almost the same, and in the other routes the speed would be higher, considering that okay for that particular period of time. So, the same way we have assumed solved the static equilibrium problem, we could have also solved the dynamic equilibrium problem, but it would have been for smaller time segments and so on. So, that is what these two approaches are, but usually the first approach is the one that is being used because it follows the simulation approach and it also is able to adjust the routes dynamically during the process. So, that is what is mostly in most of the models currently take this particular approach. And to run a dynamic assignment model, we require certain kind of information. That means there has to be some information which is conveyed to the driver, otherwise he is not going to be able to change his path, because he will only change his path if he gets the information that there is a better path. So, that means for different kinds of information, for example, as per the typology of information, that is it descriptive or prescriptive, we can say that if he gets information like congestion ahead or travel time to airport is 5 minutes, that is the descriptive information. Whereas a prescriptive information is a message VMS sign, suppose is flashes a message turn left or turn right because there is congestion ahead or something like that. So, that is a prescriptive type of information. Then in the amount of information that is available and when. So, some amount of information is available pre-trip, that could be via internet or television. Sometimes there are announcements that there is congestion along a particular corridor and so on. So, this is pre-trip information, whereas there is en route information, that is while the person is doing a trip. So, this could happen in different ways as well. That means he can be conveyed the message by a variable message sign, or it could be through a in-vehicle navigation system, like the navigation system continuously updates the route as per certain links become more less costlier, or it becomes more attractive. So, that means this in-vehicle, so that means he is getting the information during when he has already determined the route. So, in between route he is getting information. So, that is en route information. So, when we talk about the time dimension of information, there are 3 time dimensions we can consider. For example, there is a historical data, that means based on network performance in all previous time periods with similar characteristics. So, there is a certain pattern. So, like for example, if we before our travel, if I give a search even in using the Google traffic, or navigation, that what is the travel time between 2 particular zones and what should be the best path in navigation, then I will get some predictions that is based on all information which is before. That means that all situations that has happened before. So, it runs a predictive algorithm and it predicts that okay, what is the likely travel time and so on. So, this is all historical data, and based on that I can take a decision. Now, real time data or real time or current information, like en route information that we are talking about, this is information on current network conditions. That means right now what is the situation. So, even if I have started the trip, there could be a current update on the route or the congestion and so on. So, that is current information. So, this is real time information. And so, that actually, even though you get a prediction from Google, it may give you a different prediction when you are in the route somewhere. So, that is what it is. And then there is predictive or self-consistent information. So, what it means is information derived from prediction of future conditions. That means here you are predicting that okay, this is likely to happen, because not everything could be known. So you can make some guesses. If this is the situation, these are the kind of suddenly there is a, suppose there is a roadblock, so you know what is likely to be the condition. So you know that if I don't divert now, I will miss my plane. So you take a decision to divert even though it's a longer route. So this kind of decisions are actually also sort of gives you some sort of information. So these are the different information that is required to understand the different states of the entire system and of the traffic system or the network system, and based on that this dynamic assignment models can actually work. So let's see this overall process. For example, over in this particular image, you can see we have previous day and this is next day. So that means data which we get from this day becomes the initial information for the next day over here, t plus 1. So the data which was there earlier, that is t minus 1 this day, this becomes the initial information. So we, based on demand models that we can estimate for that particular, which will give us the OD matrix or the interzonal trip volume, we can decide on the different cost of different paths networks. This is the first, and then we, based on that, we can determine the expected path performances during that time period. So this is based on information which is coming from day t minus 1. And then we also get some other informations on the OD flows, and we updated path performances, and then before departure we can run this pre-departure model and we can decide on what actually would be the route assignment. So once that is done, then what happens? Then we determine the pre-trip path flows. Then some new information can come in, that is for example, over here we can see that there is en route path diversion model and then the path flow. So first there is basic information, based on that we have decided on the path, and then there is new information for which we can also again change the path en route, means during route we can change the path. So this is en route path diversion model, and then actually again the path flows are re-estimated. So pre-trip path flows and then again path flows after this en route diversions. Now how this is happening? That means this actually whenever there is a network flow, so this actually leads to the network flow propagation, and that means path flows are now loaded into the links. Then the link flow is updated, the link performance model runs. We can run a fundamental, using the fundamental equation or using any kind of link cost function, that we can determine the new link travel time and cost, and that actually again affects the network flow or propagation. And then this actually leads to the path performance model over here, and this is the data for actual path performance which goes over here, and again it is going back to over here. So even this kind of information, once it is there, so this becomes information for the next day as well, and some amount of this link travel and cost, this actually becomes en route information. This en route information or could be used by pre-trip information model to get the pre-trip info which actually modifies my initial trip, and also en route information is actually going to change this part. So that means so continuously what is happening, we are getting information even before we start the trip or during we doing the trip, and based on my information my routes the routes are determined, because I am getting information that this particular link has got a congestion, then another link has got a congestion. So we recompute the paths continuously, and once we do that, my trip volume is assigned to the particular path, and that actually leads to all, and when this is done for all vehicles and all, the network flow is determined, and from there network flow to link flow, and then link flow to again this will lead to link travel and cost, which actually determines the new path performance model or the travel time in that particular path. So that becomes en route information for some new vehicles, some existing vehicles, and it becomes pre-trip information for new vehicles joining into the system. So, this is the overall dynamic assignment process, and all this information becomes next day's expected expected path performance for the next day. So, before that gives us initial estimates for what is the travel time in the different links for the next day. So, how do we solve a dynamic assignment problem? So, usually it is done in 3 steps, and we of course within that there has to be a stopping criteria. We do it in an iterative manner, and the stopping criteria is of course we check for convergence, or there is a convergence criteria, and this convergence actually leads to this dynamic equilibrium. So, first we determine network loading. Given a set of route choices, that is routes and route flows, preliminary route travel times are estimated. So, this is the first step as we just discussed. Then we update the path sets. Given the current route travel times, the new shortest route per OD pair and departure time interval are identified. So, the route shortest pair between two origin and destination changes for each time interval, and that depends on the travel times for that particular route, for that particular links and all. And then finally, we have path assignment adjustment. Given the updated route set, vehicles or flows are assigned to routes such as dynamic equilibrium is attained. So, this is the basic steps in a dynamic traffic assignment process. So, basically we are doing the previous we are following the same procedure like route choice, link assignment, like we have already learned, but we are doing it for shorter time periods. We are iteratively doing this, and we are also checking that at one point of time within each period there is convergence of travel time between all the different smaller segments. Like for example, this is a simulation interval and this is a assignment interval. So, for every assignment interval there is a update on the total routes and travel time and all for each assignment period, and simulation interval is delta t, where what happens is a small portion of the a small portion of the entire flow during that time is assigned to that particular route segment. So, we do it for multiple groups, and based on the path information, automatically the cost information of different paths, different groups gets assigned in different proportions to different paths, and also that is based on the route choice probability for that particular group of vehicles during that particular time. So, this is simulation time interval is smaller because it is for how many vehicles or a particular flow at a particular time that has to be assigned, and assignment intervals are longer. That means after those certain times there is a update of the total network times and the paths and so on. So, we can see in this particular image. So, first we do network loading over here, and then we have, and these are the assignment intervals 1, 2, 3 and so on in this way. And we gradually, simulation interval is whenever we are doing some amount of assignment of certain vehicles into this particular links, and we are estimating the flows and all. So, first we determine arrays storing time varying travel time, intersection delay, etc. from different links. Next, path set is updated including latest time dependent shortest path, and you see this too is done iteratively in between. So, the entire process, of course, there is a feedback over here. That means one paths are adjusted based on the path set update, then automatically array storing vehicles and assigned selected paths. This part, after path assignment we have this kind of array storing vehicles and assigned path, and that actually changes the network loading, and that eventually again changes the time varying travel times and so on. But within this we have a sub loop where we can see between these two particular steps like array storing time varying travel time, intersection delay and so on. That means we are measuring the travel time, and then based on that we are updating the paths. So, this too is done iteratively for different vehicles, groups of vehicles, and until there is convergence. So, that means there is dynamic equilibrium of travel time. That means travel time becomes same for the different routes in that particular time, this particular assignment period, and then once it stops we again move to the next part. So, this actually elaborates it further. So, you can see that these are newly generated vehicles coming in at different time periods. So, this is the assignment period. So, within this period, these are the different groups of vehicles coming in, and once these groups of vehicles are coming in, so they are getting updated traffic information condition, and then they are getting instantaneous shortest path information. They update the shortest path, and this goes to newly generated vehicles for this time period. Like if I am sending this information over during this assignment period, it goes to newly generated vehicles which is joining during this time period. So, this becomes their pre-trip information, and for en route info vehicles, it becomes the information which they will use to update their routes or the choice of routes. So, in simulation approach, we regularly update and assign shortest routes based on prevailing traffic conditions to newly generated vehicles at the start of the trip, and in addition, en route vehicles or a subset of vehicles re-evaluates. That means vehicles which belong to that particular group. That means that simulation time, I said that there is a small simulation time within that whatever group of vehicle is considered. So, that subset of vehicles is re-evaluates the current route at each decision node based on current instantaneous link travel times, and then they update their particular route choice. So, this happens continuously for each assignment time period, and automatically we come to a point when there are during each assignment time period there is equilibrium that is being there is equilibrium and dynamic equilibrium, and then we move on to the next time assignment period. So, this is how the simulation proceeds. So, just to take you through the different steps of the simulation in detail, first we need to calculate the initial shortest path for each OD pair using the defined initial cost, that is standard procedure, and then we evaluate the initial cost function for each link j, and j is subset, j is one link among all the links, and cost of j is the initial cost that we consider, and apply the shortest path. Then we use the route choice module, and we apply the shortest path routine for each destination centroid D. That means for reaching every point D, we calculate the shortest path tree from every other origin, and that we actually save. And this is the then identify the shortest path from the shortest path tree for each OD pair from origin centroid to destination, and add this path to SPCon to Ki. So, SPCon is that, so that path S is added to this, the shortest path tree, this SP, this one. And see, then in step 1, once we have done that, so this is the first step, we initialize the simulation. Then in step 1, we simulate for a predefined time interval delta t, that is that small time interval that we talked about, and assign a fraction of the trips to the available path Ki. That small group of vehicles are assigned to the available path Ki between OD pair for delta t as per probability Pk into k, that is Ki which is a subset of Ki estimated from route choice model. That means there are suppose 3 routes in the shortest path, and 3 shortest path actually, and then these are k shortest path. That means we for each OD pair we measure this 3 shortest path, the first 3 shortest path, and then we have a probability for assigning vehicles to each of the shortest path, and based on this particular during delta t time period, whatever vehicle fraction is there, we will assign it to using this probability to each of this shortest path. And then after the assignment is over, we determine the new average link travel time, and this is used, and that is obtained during the simulation process. Then in step 2, what we do is we update the link cost function because new travel time has come in, and cost j is now the dynamic cost j because we are updating it, it is changing, and then based on this new cost, we calculate the shortest path tree SPTD for each destination centroid D using cost, same thing that we have done earlier, and then we identify the shortest path for the shortest path tree for each OD pair I. So, again the same thing, and we add the path SPCon to Ki. So, this new path is being added. Then we can assume that, once that means first we have based on previous information we assign the vehicles and based on the delta t time period, a fraction of vehicles is being assigned, and then we update the travel time, and once we do that, we get new shortest path and all. Then this new shortest path information is sent using variable message sign and other channels, maybe internet or navigation system, to drivers. So that using that information they can dynamically change their route, reroute, and once that happens, then we can then do preventive dynamic assignment that we have already discussed, like if all the demand and then they can update their routes, and then we can also do reactive dynamic assignment as well. I'll just go back to the previous slide. So here I missed something. So there is a point called decision node. So each driver during once he gets en route information, so what he does, he reevaluates the current route at each decision node. So he does it at a certain point. That means it could be a intersection from where he has option to diverge. So at each decision node, he will take that decision. He doesn't take it just like whenever he is just during any point. So it has to be a certain point. So once he gets the en route information, so then he takes a decision at a particular decision node, and then he may divert to a different route. So then once that route choice is done, then that means that diversion into a new route will happen from this particular decision node. Then we can either do preventive dynamic assignment or we can do reactive dynamic assignment. Reactive dynamic assignment we will solve using the equation. We will equate the different travel times for different group of vehicles, and then we will set equilibrium, and like we have solved earlier equilibrium solution. Or it could be preventive dynamic assignment like we just discussed in the previous step. Like we will update the travel time, we will do those diversions from that particular points, they will assign into new routes, and then again the travel time, everything will get updated and so on. So this is the two steps that we can follow once this new information is updating the travel time information, and new routes and everything could be calculated and so on. So this is the simulation procedure. Some important parameters which are used in the simulation. One is the cycle parameter. This parameter defines the time interval delta t used in used during this particular assignment process, and it is the interval between recalculations of the shortest path. So after each of this interval, we will recalculate the shortest path, and then this time interval is used to evaluate R gap function. This relative gap function is the one which is used in the convergence criteria. So basically R gap is the ratio of the total gap, that is how far the current assignment solution is, how far it is from the ideal shortest route time. That means to the total shortest, it is the ratio of the total gap to the total shortest path time. So that is what it is, and this is how, and what this total gap means how far away is the current assignment solution to the ideal shortest time. So that is how we are going to measure the total gap, and the ratio between total gap and the total shortest path time is the R gap. So when that value reaches a certain value, then we say that we have reached dynamic equilibrium. So then comes the number of intervals. Dynamic cost function of each link is evaluated using data observed during the simulation, that is link travel times, from the last number of intervals as said by the cycle parameter. So this number of this cycle parameter over here, it actually determines that how many intervals are going to be there and how many intervals will be kept in memory. That is what is being considered over here. Then the capacity weight, it is a user-defined parameter to control the influence that the link capacity has on the cost in relation to travel time. So this is the weightage of that particular link. And then route choice model, this parameter determines the discrete choice model used during the simulation. Different route choice models are used. It could be proportional. We can proportionally divide the fractions of trips into the different route choices, or it could be a logit model as we have already discussed earlier, or it could be a conditional logit model. or it could be a user defined root choice model based on any other strategy that the user undertakes. So, this is the root choice model. And then we also need to understand how many shortest path we are going to save. So, this KSP parameter defines the number of shortest path trees calculated per destination. This is also determines the amount of that means how the vehicle fraction should be divided amongst the route. Then maximum number of SPT, that is how many number of shortest path tree per destination are kept in memory during the simulation. So, that is another parameter. So, this saves memory and improves the performance. And then maximum number of routes, that parameter also defines the maximum number of different paths used in the path selection process. So, these are the different. So, for each link for each destination pair we have a shortest path, and then we have got different paths that is actually stored. And then finally, we have model validation. So, once we have run the simulation, we need to validate our model. So, we calibrate the model, and what we do is we take the model inputs and the parameters resulting in the output, and we check how closely they match with the field observation for that particular time period of that particular day. Now, what kind of parameters are checked? Like for example, using these vehicle detectors like induction loops and so on, we can check how many vehicles are there in a particular link or in a particular link, in a particular lane, what is their average speed and during in that lane. Then average link or segment density, that also could be measured at that detector location, or queue lengths and intersection turning movement counts, these also could be evaluated. So, these are the things that are checked in the real world, and then from the model also we check those parameters, and if those two more or less matches, then we say the model is valid and it is also calibrated in this particular order. So, these are some of the references you can study. And to conclude, DTA allows dynamic network equilibrium modeling, which is not possible in static traffic assignment. DTA models can be used for real-time operational control of traffic systems and for operational planning, such as evaluating the effect of two-way to one-way configuration in CVDs, like highway expansions, bypass construction, and also for evaluating travel demand management strategies such as peak spreading or congestion pricing. So, this kind of assignment actually helps in to evaluate these strategies like peak spreading or congestion pricing and so on, because that will help us to determine what kind of what kind of travel times will result because of this congestion pricing and all, and that actually helps us to understand travel demand eventually. And then DTA models are mainly used to estimate dynamic traffic flow patterns like system level travel time, miles traveled, and stop times. And additionally, time dependent link travel time, speed, densities, queues, and stop times could be also estimated using this kind of model. And we calibrate DTA model, and it's the most critical step. And simulation based DTA models do not strictly conform to properties such as uniqueness or equilibrium in most cases. That means we are not able to achieve equilibrium perfectly. So, to some extent we do achieve that. So, that is how this we can this dynamic traffic assignment is actually helps us in getting real time information of different links, or we can model the real time information what will happen. And that is how it is replacing the normal static equilibrium process gradually, because these are very intensive models and data intensive and all, but we have enough computational power to actually solve this kind of models now. Thank you.